Hello guys. So in this video we will discuss about the chapter time series analysis. The first learning outcome statement is calculate and evaluate the predicted trend value of a time series modeled either as a linear trend or a log linear trend. The second statement is describe factors that determine whether a linear or a log linear trend should be used with a particular time series and evaluate limitations of trend models. So let's discuss what's the difference between a linear trend model and a log linear trend model. In a linear trend model, your time series should look like this. Like there is a constant amount of change with time. That is called as a linear trend model. If your time series looks like a straight line with respect to the time, then you can use a linear trend model, and a linear trend model is modeled as y is equal to b naught plus b1 times t plus epsilon t. This is the error term here. And if your time series looks like this exponential growth pattern here, then you can model it as a log linear trend model, and the log linear trend model is defined as y is equal to e raised to the power b naught plus b1 times t plus epsilon t. It can also be written as log n y is equal to b naught plus b1 times t plus epsilon t. Epsilon t here is the error term. And what are the limitations of linear trend model and log linear trend model? The time series models generally have serial correlations, like the error in one particular time period is related to the error in the next time period. So the single variable regression such as trend models do not correctly specify the time series, and we can use DW test to check for the significance of the serial correlation. If the DW stat is lower than the lower bound, the critical lower value of DW stat, then we can say that the serial correlation exists. And if a serial correlation exists in the data, you cannot use linear trend model or log linear trend model. So this explains the learning outcome statement B. Describe factors that determine linear or log linear trend model should be used. For the learning outcome statement A, calculate and evaluated the predicted trend value. Suppose you are given two models. You are given a model like is a linear trend model with b naught is equal to 5 and b1 is equal to 2. Then the y is equal to, and you have to find the value at t is equal to 2. So then y is equal to b naught plus b1 times t. B naught is 5 plus b naught is 2 times 2. It comes at 9. Similarly, for log linear trend model, you are given b naught is equal to 5 and b1 is equal to 2, and you have to find the value at 2. Then log n y is equal to 9, same value, and y is equal to 8103. So that's how you calculate the values for linear trend model and log linear trend model. So let's come to the next learning outcome statement. It says explain the requirements for a time series to be covariance stationary. So what are the requirements for a time series to be covariance stationary? First of all, the expected value of the time series must be constant and finite, and the expected value is also the mean of the time series. So the mean must be constant and finite for that time series to be covariance stationary. The variance of the time series must be constant and finite. The covariance of the time series with itself for a fixed number of periods in the past or future must be constant and finite in all periods. So the variance should also be constant and finite, and the covariance of the time series with itself must also be constant and finite in all periods. If any time series satisfies these three requirements, then we say that the time series is covariance stationary. And we also have to describe the significance of a time series that is not stationary. For a non-covariance stationary time series, estimating the regression will yield spurious results the estimate of B1 will be biased and any hypothesis test will be invalid. Basically, if you have got a non-covariance stationary time series, you cannot use any regression to actually calculate the model. And there are the next type of model that we want to discuss is AR model, the auto-regressive model. Basically, we need to be able to describe the structure of an AR model of order P and calculate 1 and 2 period ahead forecast. Then we need to explain how the autocorrelations of the residuals are used to test whether AR model fits the time series, and explain the mean reversion and mean reverting level we need to calculate. So these learning outcome statements are depending upon one another, so we will discuss them together. First of all, we need to be able to define the structure of an AR model. Let's see what an autoregressive model is. In an autoregressive model, the independent variable is the past value of the dependent variable. So the yt, the dependent variable, is equal to b0 plus b1 times yt minus 1. This is the past value of dependent variable plus epsilon t. Epsilon t is same as the error term. So this is called as AR1 model because we are using one lag value of y. So that's why it is called AR1 model. Now to define an ARP model, that is that we need to take the previous p values as lag variable. Yt is equal to b0 plus b1 times yt minus 1, and similarly up to bp times yt minus p plus epsilon t. So this is an ARP model. Now how to test if AR model is correctly specified? To test the significance of an AR model, first of all we will estimate a particular model. Let's say we estimated an AR1 model. We will compute the autocorrelations of the residuals and test to check if autocorrelations differ significantly from 0. If autocorrelations differ significantly from 0, the model is not correctly specified. This error here, the autocorrelations differing significantly from 0, is called the serial correlation of AR model. That is, the error terms are depending upon one another. Also, we cannot use DW test with an AR model. You need to remember this. This is quite an important concept. Like from the testability perspective, they can give you a DW stat with an AR model and ask you whether a serial correlation exists or not. You need to remember that the DW test is not usable with AR model. And let's come to this is how to test for the significance of the AR model. Now let's discuss the mean reversion level. A time series shows mean reversion when it tends to fall if it is above the mean. If it is let's say this is the mean of the time series, if the value lies here, the next value will tend to fall, and if the value at previous period was here, the value will tend to rise to the mean level. So this is like the value is fluctuating around the mean itself. So that time series is called to be shown mean reversion. Now how to calculate the mean value? Now we know that at this particular mean value, yt will be equal to yt minus 1 because the expected value is always equal to the mean value. So the yt is equal to yt minus 1 to and if we put this into our AR1 model, times yt. Now if we calculate for yt will be equal to b0 divided by 1 minus b1. So this is our mean reversion level, b0 divided by 1 minus b1. And from the testability perspective, what could happen is like you will be given the different values of b0 and b1 and you will be asked to calculate the mean reversion value. So you need to remember this formula. Now let's discuss the next concept, the chain rule of forecasting. For AR models, suppose you are given a particular model and you are given a suppose you are given a value of yt, you may be asked to calculate the value at yt plus 1, value at yt plus 2, value at yt plus 3, and so on. Basically they will ask you to calculate the value up to t plus 2. So how to do that? Suppose you are given the intercept value, that is b0, and you are given the slope coefficient, that is b1, and you are also given the current value of y. So the current value of y will be used to calculate the value at yt plus 1, and the value that you calculated for yt plus 1 will be used to calculate the value at yt plus 2. That is called as chain rule of forecasting. You are using one value to calculate another, and then using that value to calculate the next value. Now see, yt plus 1, let's say we are given these values and we need to calculate yt plus 1 is equal to intercept 0.5 plus slope coefficient 2 times the current value of y, which is 5. So the answer comes at 10.5. Now you use this 10.5 calculated value to calculate the value of yt plus 2. Yt plus 2 is equal to 0.5, the intercept term, plus 2 times 10.5, and it comes around at 21.5. So this is the chain rule of forecasting in AR models. Now let's discuss the next learning outcome statement. Contrast in sample and out of sample forecasts and compare the forecasting accuracy of different time series models based on root mean squared error criteria. In sample forecast errors are the residuals from a fitted time series model. The out of sample forecast are the difference between the actual realized values and the predicted values of the model. So those are the out of sample forecast errors. Now how can we check, how can we compare the accuracy of two different time series models? We need to compare their root mean squared errors. Now let's see, you have got observations up to t. So for these t observations you will have t actual values, and t predicted values. Now let's see how to calculate the root mean square error. Root mean square error is equal to actual value for I minus the predicted value for I, square this. We need a sum of I is equal to 1 to t, because we have t different observations. So for each observation we calculate the error term actual I minus the predicted I, then we calculate the square value of those errors and add those errors, calculate the mean value divided by t, and then calculate the square root of this mean error. This is the root mean square error, the square root of the mean of squared errors, square root of the average squared error. So that is your root mean square error. A model with lower root mean square error is required. So if you are comparing two models, one is having a lower value of root mean square error, that model performs better than the one with a large value of root mean square error. Now let's see the instability of coefficients of time series models. See, the coefficients can change depending upon the sample period that we are using to calculate the model values. The coefficients can be different for earlier data period versus the later data period, or they can also differ between if you are using a longer data period and a smaller data period. The guidance is we look at the graph of the time series and then see if the particular data period looks like, just as in this graph, the period 1 data looks different from the period 2 data, although it depends, although it is the data for us for the same time series, but the variance and the mean values for period 1 are totally different from the variance of the period 2. So we can say that the period 1 was per one particular time period and the period 2 is a different time period, like a different regime, you can say a different regime. For example, according to the financial perspective, let's say one particular this was the time period with the restrictive financial policy, you can say restricted financial policy, and this time period is for expansionary financial policy. So we know that both of these time periods will have different characteristics, so we cannot use the coefficients predicted using period 1 to calculate values of period 2, because the characteristics of period 2 have changed. Period 2 is an expansionary phase, so period 2 will have different values of coefficients. That's how you determine whether to use this particular data or not. So to calculate the coefficients, you have to determine like which data period to be used to train your model. Now let's come to the next learning outcome statement. It says describe characteristics of random walk process and contrast them to covariance stationary process. A random walk is a time series in which the value of the time series in one period is the value of the series in the previous period plus an unpredictable error term. This is a random error, so the expected value of the error term is 0 and the expected variance of the error term is sigma square. The covariance of the error terms of two different periods is 0. So you basically need to remember this, that a random walk is simply the value of the dependent variable in the previous period plus an error term, so that the value fluctuates like this. This is a random walk process. A random walk has what are the characteristics of random walk? A random walk series has no defined mean reverting level. The random walk has no mean level. Xt is, we know from the AR1 model that the mean reversion level xt is equal to b0 divided by 1 minus b1. In this case, b0 is 0 and b1 is 1. The slope coefficient of the previous lag term is 1 here. So the mean reversion level comes at 0 by 0, which is not defined in mathematics. So a random walk series has no defined mean reverting level, and the variance of a random walk is increases with respect to time. For any period t, the variance of xt is equal to t minus 1 sigma square, because for each and every term the error terms keep on adding itself. So as the error term is getting larger and larger, the variance of the error term is also growing. So as t grows large, so does the variance of the error term. Therefore, since the variance is also not constant and there is no mean reverting level of the random walk, a random walk series is not covariance stationary. A random walk series is not covariance stationary, so we cannot use standard regression analysis on a time series that is a random walk. So now you know that you cannot use regression analysis on a random walk. Then let's discuss the implications of unit roots for a time series analysis. These three learning outcome statements are interrelated, so we will discuss them together. Describe implications of unit roots for time series analysis. Explain why unit roots are likely to occur and how to test for them. Demonstrate how a time series with a unit root can be transformed so it can be analyzed with an AR model. Describe the steps of the unit root test for non-stationarity and explain the relation of the test to AR model. Now let's discuss the unit roots. We know that AR1 model is yt is equal to b0 plus b1 times yt minus 1. If b1 is equal to 1, if the slope coefficient is equal to 1, the yt becomes yt is equal to b naught plus yt minus 1. This is a random walk with drift term. This b naught is known as the drift term here, and it has become a random walk. Now we know that a random walk is not covariance stationary, and we cannot use regression analysis with random walks. So therefore we need to kind of transform this series so that we can use regression analysis. And how to test for the unit roots? There is a Dickey-Fuller unit root test that we can use to test the unit roots in a time series. How to do that? We define that series as yt is equal to b naught plus b1 times yt minus 1 plus epsilon t, the error term here. We subtract yt minus 1 from both sides. So the left hand side becomes yt minus 1 is equal to b naught plus b1 minus 1 times yt minus 1. We replace the b1 minus 1 with g1. So the g1 is equal to b1 minus 1. What we will do is we will regress this particular time series here and check if the value of g1 differs significantly from 0 or not. If we fail to reject the null hypothesis that g1 is equal to 0, if we fail to reject the null hypothesis, then we know that g1 is equal to 0, which means b1 is equal to 1, so a unit root exists. So if b1 is equal to 1, we know that it is a random walk series with a drift, so we cannot use the regression analysis on our AR1 model. So how we can transform a unit root or a random walk series? We transform it using first differencing. What is first differencing? We subtract the lag term from both sides of the equation. So yt is equal to yt minus 1 plus epsilon t. This is our random walk. We subtract yt minus 1 from both sides. So the left hand side becomes yt minus 1 is equal to epsilon t. We can say that xt is equal to yt minus 1, a new term. Now we know that the expected value of epsilon t is 0, the error term, expected value of the error term is 0, so the expected value is 0, and the variance of epsilon t is sigma square, and the covariance of this is 0. So the best forecast for xt at 0 is xt is equal to 0, so yt is equal to yt minus 1. So the best estimate that we can make is there is no change in the value of the current time series. Now since the expected value of epsilon t is 0, so this is a covariance stationary time series. How we can check? First, the mean reversion level is constant. The mean is constant with epsilon t. Expected value of epsilon t is the mean value of the series, right? The mean value is 0 here, it is a constant, and the variance of the time series, the expected variance of the time series is also constant, sigma square. It does not depend upon t. So therefore our first differenced time series is covariance stationary, and we can use the regression analysis here. Let's discuss the next learning outcome statement. Explain how to test and correct for seasonality in a time series model and calculate and interpret the forecasted values using an AR model with a seasonal lag. Now, how we can check the seasonality? We can check the autocorrelations of the error autocorrelations of AR model. If one particular autocorrelation is very high compared to others, we can say that the time series has a seasonality problem. Suppose we are regressing the sales of a particular company with time, and the graph looks like this. From the graph, it is very clear that at a particular time the sales dip and then recover immediately. The sales dip, recover immediately. So it is, this pattern is repeating. So we can say that there is a seasonality term, like in a particular, so you can say like in the holiday season the sales dip and then picks up regularly. It could be like the company could be providing stationery items to schools. So during the holiday season the sales go down and then they recover as the schools reopen. So how to check the seasonality? Suppose this table gives us the error autocorrelations of the model. So if you can check, the fourth correlation is very high whereas others are very low. So we can say that their fourth correlation is significant, and there is a seasonal problem in this AR model. Now how to correct that seasonality problem? The autocorrelation that is very high with respect to others, the autocorrelation was the fourth autocorrelation, that the fourth lag autocorrelation. So we know that the seasonal lag is the fourth lag of the model. So we add that lag value also in the model as independent variable. So now the sales T is dependent upon the sales on the quarter before, and also the sales on 4 quarters before, the sales T minus 4. So now if we see, the autocorrelations are very low. Not just the fourth autocorrelation, the other correlations also are down. So we know that we have estimated a correct model. To calculate the forecasted value, you will be given the sales at T minus 1 and sales at T minus 4, and you will be asked to calculate the sales T value. So that is a simple concept here. Now let's see what is an autoregressive conditional heteroscedasticity and how the ARC models can be used to predict the variance of a time series. Now heteroscedasticity is the dependence of the error term variance on the independent variable. The error term variance depends upon the independent variable. It results in incorrect standard error of the regression coefficients. When variance of the error in a particular time series model in one period depends upon the variance of the error in previous periods, the variance of the error in one particular period depends upon the variance of the error in previous period, it is called autoregressive conditional heteroscedasticity. And how we can test for ARC model? We will regress the variance of the time series on the variance of the error in a previous period, and we check if the estimate of A1 is significantly different from 0 or not. If A1 differs significantly from 0, we know that the variance of the error term at time period T depends upon the variance at time period at T minus 1. Therefore, our model is ARC1, autoregressive conditional heteroscedasticity model at 1. And if we know that our model is ARC1, how we can use that to predict the variance? The variance of the error at T plus 1 is simply predicted as A0 expected, the predicted value of A0 plus the predicted value of A1 times the epsilon T square. So because we know that it is an ARC1 model, so the variance of the error at time period T plus 1 will be depending upon the variance of that error at time period T. So we can calculate it like this only. Up till now, what we have done is we have calculated used regression analysis to predict the values of one particular time series where the independent variables were constant or the lagged values of the same time series. Now, what if the independent variables are different time series? Different time series, suppose you are predicting the time series of profit and regressing this time series on the sales. So sales itself is a time series and profits are also a time series model. So when you are regressing one time series on another time series, you need to check for non-stationarity and the co-integration of time series with each other. How we can use the how we can test the non-stationarity? We can use the Dickey-Fuller test to check for non-stationarity and unit roots. Now if there are no unit roots, say we were using two time series models here, both of these time series have no unit roots, then our regression is valid. We can use the regression analysis to predict the profits depending upon the sales. But let's say one time series has unit roots and the other does not have unit roots. The sales are a unit sales time series has unit roots, whereas the profit time series does not have unit roots. In that case, your regression is invalid. We cannot use regression analysis in this case. The third scenario is when all the time series, both of these time series have unit roots and they are co-integrated. How to check for co-integration? We will discuss that in the next step. But let's see, the time series have unit roots and they are co-integrated. In this case, your regression is going to be valid. But if the time series have unit roots but they are not co-integrated, then your regression will not be valid. So how we can check for co-integration? What we will do is, we will estimate the following regression for two time series. Yt is equal to b0 plus b1 times xt plus epsilon t. Now we need to check whether the error term in the regression, the error term has a unit root or not, using the Dickey-Fuller test. If the error term has a unit root, the error term is not covariance stationary and the time series are not co-integrated. But if the error term does not have a unit root, the error is covariance stationary and we can conclude that the time series are co-integrated. So that is how you can test for co-integration. The next learning outcome statement is determine an appropriate time series model to analyze a given investment problem and justify that choice. See, what I would recommend is you read this particular learning outcome statement topic from the curriculum itself, because the curriculum is explaining it very well. So I won't be able to do justice to the reading here. It's just a small reading that explains the topic very well. So I will recommend you to go through the curriculum for this particular learning outcome statement. Thank you.